Hi, welcome to your Mac 200 Statics online classes. Today we're going to start chapter 3. This is the first of a series of 3 videos in which we're going to study the conditions necessary to keep a particle in equilibrium. I hope you enjoyed this video. Let's start by highlighting the objectives of this chapter. Basically, we have two main objectives here. First, we are going to introduce the concept of free body diagram for a particle. As we see, such diagrams are very important to identify all forces acting in a particle. And finally, we're going to show how to solve particle equilibrium problems using the equations of equilibrium. Let's start by verifying the conditions required for the equilibrium of a particle. We remember from chapter 1 that Newton's first law of motion assures that a particle is said to be in equilibrium if it remains at rest, which is also sometimes referred as a static equilibrium, or if that particle moves at a constant velocity. More specifically, the equilibrium condition is applied by using the mathematical form of Newton's first law of motion, which basically states that the sum of all forces acting on that particle must be equal to 0. And that's the only general equation we need to do whatever calculations in which a particle is to be maintained in equilibrium. In order to apply the equilibrium state equation to solve practical problems, we need to understand first the concept of free body diagram, which we use to account for all known and unknown forces acting in the particle. The best way to do this is to think of the particle as isolated and free from its surroundings. That's why the term free body diagram. And just to make it clear, by unknown forces, I mean that we are going to consider only the forces that we know they are there, but we don't know their magnitude and direction. Let's take this example here, in which we have a bucket held in equilibrium by a cable. For this case, our judgment tells us that if this system is supposed to stay in equilibrium, whatever the tension acting in the cable, it must be equal to the weight of the bucket. By drawing the free body diagram of the bucket, we can easily visualize this equilibrium condition. This diagram here shows the two forces acting on the bucket, and since we're assuming that it can be modeled as a particle, we can simplify its geometry in the free body diagram and include the x and y axis. From the equilibrium state equation, the resultant of these two forces must be equal to 0, which gives us the mathematical expression that T is equal to W. Let's talk now about 3 types of supports typically found in particle equilibrium problems. The first one is a linearly elastic spring, which has undeformed length L0, and when submitted to a pulling force F, we'll get the elongation distance S, resulting in a final deformed length L. For this case, if a particle is pulling the spring on, we can write the equilibrium condition for the spring through this linear equation, in which we consider the quantity K, that is the spring constant or stiffness, and the elongation distance S. On the other hand, if the particle is pushing the spring, then we have a compression distance defined by minus S. Let me give you one numerical example of this. Let's say that we have a spring with undeformed length of 0.8 meters, stiffness of 500 newtons per meter, which is elongated to 1 meter after the application of a pulling force F. We can calculate the elongation distance of the spring by taking the difference between its final and initial lengths, and then we apply the equilibrium state equation to calculate the magnitude of the pulling force, which for this case is 100 newtons. Cables and pulleys belong to another important class of supports commonly found in statics problems. We consider here several assumptions for them, at least for now. Among those assumptions, we consider that cables have negligible weight and they cannot stretch. Also, a cable can support only a tension or pulling force, and this force always acts in the direction of the cable. We will also assume here that for a continuous cable in equilibrium, the tension force acting on that cable has constant magnitude throughout its length. And lastly, we assume that there is no friction in the contact between the cable and the pulley. Another important class of supports regards smooth contact surfaces, in which an object rests over a smooth surface. In this case, the inclined surface exerts a force on the cylinder that is normal to the surface at the point of contact, and the cylinder is subjected to its weight and the tension force of the cord. Since these three forces are concurrent at the center of the cylinder, we can assume that the cylinder is a particle and apply the equation of equilibrium to this particle. Since we must account for all forces acting on the particle when applying the equations for equilibrium, let's establish here the steps necessary to construct a free body diagram. First, we have to focus on drawing the particle's outline shape, which requires removing all supports that hold that particle. Next, we have to indicate on this sketch all forces that act on the particle. And finally, we have to identify each known and unknown force according to their magnitudes and directions. Let's take, for example, the 5 kilograms plate suspended by two straps A and B as shown here. To find the force in each strap, we should consider the free body diagram of the plate by drawing first the outline shape and then representing the acting forces, which are the tension in the straps A and B and the weight of the plate. As we can note here, the three forces acting on the plate are concurrent at its center, and we can further simplify its geometry just like this to highlight the forces in the free body diagram. Now, let's work on one example of how we should draw free body diagrams for typical statics problems. In this example 3.1, we have a sphere with a mass of 6 kilograms that is supported as shown in this figure here. Then we are asked to draw separate free body diagrams for the sphere, for the chord CE, and for the knot at C. In order to do this, remember that we have to draw the outline shape first, and then identify all forces acting in each one of the requested components. Let's start with the sphere, in which we draw first the outline shape. Observe that the identification of all forces acting on the sphere requires careful attention on how the sphere interacts with its surroundings. After this exercise, we can identify 4 main forces acting on the sphere, which are the force FCE caused by the tension on the cord that pulls the sphere on, the 2 normal forces coming from the reaction with the smooth inclined planes, and the weight of the sphere, which can be readily calculated from the mass and the gravitational acceleration, resulting to 58.9 newtons. And this is the complete free body diagram for the sphere. With this diagram, we have everything we need to apply the static equilibrium equation and calculate, for example, the tension through the cord. Now, let's go to the forces acting on the cord CE. We basically follow the same procedure, in which we draw the outline shape and isolate the elements from its surroundings. Essentially, we have 2 forces acting on the cord CE, one coming from the sphere and another one coming from the knot. We can see here that since we're dealing with a cord, these 2 forces must be equal and act in opposite directions to pull the cord and keep the tension on it. And we already assumed here that cords can support only tension loads. For the last element, we have the knot C, which following the same procedure, we find out that it is subject to 3 forces. We have the force of the cord CE acting on the knot, which is a consequence of the weight of the sphere transmitted as a tension load to the chord CE. We have the force of the spring, which can be calculated from the expression involving the stiffness of the spring K and the elongation or compression distance of the spring. And we also have the force of the chord CBA, inclined 60 degrees from the horizontal line, which interacts with the pulley at B and the fixture at A. And that's the end of the first part of chapter 3. Thanks for watching, and I'll see you in the next video.